Hello students, I am Jisha Mary Jose, Assistant Professor from the Computer Science Department of Rajagiri School of Engineering and Technology. In this lecture, we will be dealing with some of the topics from Computer Organization and Architecture, a course under KTU for the 4th semester Computer Science and IT students. The topics to be covered in this lecture will be from Module 3, Interface Circuits. The main contents that are being discussed in this lecture have been listed below. Continuing with the discussion on input-output organization of a computer, here we are going to discuss about the various interface circuits that can be used in a system. So first we will define what is meant by an interface circuit. An interface circuit consists of the various components that are required to connect an input or an output device to a computer bus. On one side of the interface circuit, there will be different bus signals available, which can be either used for providing the data, the address, or the control values. And on the other side of the interface circuit, there will be a data path available through which we can provide the data from the device, whether it be an input device or an output device, to the processor or vice versa. And this side of the interface is called a port. And ports in an input output organization of a computer are of two types. They can either be a parallel port or they can be a serial port. A parallel port, as the name indicates, will transfer data in the form of a number of bits. That is, it can either be an 8-bit parallel port or a 16-bit parallel port. If it is an 8-bit parallel port, 8 bits of data can be taken from a device to the interface circuit at a time. Next one is serial port. A serial port will transfer and receive data only one bit at a time. Okay, that is the basic difference between parallel port and serial port. Now this parallel port and serial port is used for communication between the interface and the IO device, whereas whether I am using a parallel port or a serial port, the communication from the interface to the processor always remains the same. That is, the processor communication with the bus or the interface will be same for both kinds of ports. Okay, the parallel port can use a multiple pin connector and a cable with as many wires as the number of bits are transferred. As I already mentioned, if I am using an 8-bit parallel port, there will be 8 wires available for transferring 8 bits at a time to a device or from a device. Whereas if I am using a serial port, there will be only a single pin connector between the device and the interface circuit. The various functions of an input-output interface can thus be summarized as the following. First one, it provides sufficient storage buffers for storing the data that is to be sent to an input-output device or coming from an input-output device. Then it can contain various status flags for access by the processor so that the processor can check whether the device is now providing some data or some data needs to be sent to the device or not. All that can be checked by using different status flags which are maintained inside the interface circuit. And it also provides various address decoding circuits which can be used by the processor to correctly identify an input output device. Then it generates appropriate timing signals for bus control, that is when to provide a certain control signal or when to not provide a different timing signal. All these things can be controlled by providing various timing signals which are done by the interface circuit. And also if there are any format conversions required, for example in the case of a parallel port, there is no need of any format conversions. Parallel data is available, it can be provided parallelly to the processor, whereas in the case of a serial port, data is coming in a serial format. Now that data needs to be converted to a parallel form to be provided to the processor. So all these kinds of format conversions can also be done inside the IO interface. So these are the different functionalities that are provided by an input-output interface circuit. We will start the discussion about interface circuits by first considering an example of a parallel port. In this diagram, we can see the different components that are involved in connecting a processor to a keyboard, that is an input device. So what are the different components? We will discuss that first. Okay, now we can see that some of the assumptions given here is that the keyboard is connected to a processor using a parallel port, and some of the specifications of the processor are that it is a 32-bit processor, that is it uses 32-bit bus connections to connect to an input output device. And the other assumptions are the processor uses a memory mapped input output configuration and also an asynchronous bus protocol. Asynchronous bus protocol means different handshake signals like master ready and slave ready signals will be used for communication between the device and the processor. Now, what are the different components involved? First, we have the keyboard. The keyboard is a mechanical keyboard which contains various switches, mechanical switches, and if you press a key on the keyboard, the circuit involved with that corresponding switch will be closed and an electrical signal will be generated, which will be identified by another device or another component called the encoder, and this encoder will generate the corresponding ASCII value of the key that is pressed on the keyboard. So that is the functionality of the encoder in the second block. Then we also have a debouncing circuit over here, which is used to negate the occurrences of multiple bounces that can occur in the case of a pressing of a key. Okay, then we have the input interface that is used for this corresponding keyboard. It involves different components like data in. Data in is the input buffer register that is used inside the input interface for collecting the data that is coming from the keyboard, which is to be provided to the processor later. Next one is SIN. SIN is a bit which is used to indicate whether the keyboard key has been pressed or not. When nothing is pressed on the keyboard, the value of SIN will be 0, and when some key is pressed on the keyboard, the value of SIN will be set as 1. The input interface also contains some other components like the address decoding circuits and also bus control timing signal generators, which are not shown in the diagram, but it is there. Okay, now on the processor side of the interface, the different signals that we can see are the address bus and data bus. Address bus is used by the processor to correctly identify a keyboard by providing the address of the keyboard on that corresponding bus. Data bus is used by the keyboard to provide the data, that is the ASCII value of the key that is pressed on the keyboard will be sent from the keyboard to the processor through the data bus. Then there are some control signals like R bar, W bar, or read or write control signal. When the keyboard is used, it is basically a read operation, that is this R bar, W bar signal will be set to 1, and the two handshake signals that are used by the processor and keyboard to communicate with each other are the master ready and slave ready signal. When the processor is ready for communication with keyboard, master ready signal will be set as 1, and when the keyboard is ready to communicate with the processor, the slave ready signal will be set as 1. Now there is one more signal called the valid signal. This signal is set to 1 only when a key is pressed on the keyboard, and when the value of valid bit is set as 1, only then the SIN bit in the input interface will also be set as 1. So these are the different components that are involved in communication between a processor and a keyboard. We have the keyboard, the mechanical keyboard with a different number of switches or keys. Then we have the encoder and the debouncing circuit, which is used to generate the ASCII value of the key pressed and to prevent multiple bounces of a key. Then we have the interface, which itself involves the data in buffer register, the SIN status bit, and various address decoding circuits and timing control circuits, and the processor with the corresponding communication lines with the keyboard. So this is a circuit which explains the input interface that is used between the keyboard and the processor. Before studying the working of the circuit, we will see some of the important parts of the circuit. Here you can see the read signal or the read bar, write bar signal coming from the processor, the master ready signal that is coming from the processor, and as I have already mentioned, the processor uses a 32-bit address line which includes A0 to A31. Out of this A0 to A31, A1 to A31 lines will be used for providing the address of an input or output device. That is why only these 31 lines are connected to the address decoder, and if it is correctly identifying the address of the keyboard, then that this output line will issue a 1. Okay, and this A0 line of the address bus of the processor is specifically used for reading the status or data from the input interface to the processor. I will explain how. Okay, now we will start the explanation. That is, here you can see the data that is coming from the keyboard will come in the form of parallel data D0 to D7 to the data in register of the input interface, and the data in registers values can be taken out through Q0 to Q7 to the processor bus lines through some three-state drivers. Now what is a three-state driver? It is a specific driver which will allow the input to be placed onto the output only if this driver is activated by a third signal. And what is the requirement for activating these drivers? Here you can see there is an AND gate that is connected to drive these three-state drivers, and the AND gate has got 4 inputs. Only if all these 4 inputs are active, then these drivers will be activated. So what are the conditions? The read signal coming from the processor should be 1. The master ready signal coming from processor should be 1. The address lines should contain, that is A1 to A31 should correctly contain the address of the keyboard, and to be, if it is correctly decoded, this third line will also contain a 1. And when I am reading the data from a data in register, the A0 bit of the address bus will be set as 1. Only if all these 4 conditions are satisfied, this AND gate's value will be 1, and thus I can read data from the input interface, and that is how this drivers will be initiated, and if any data is available over here, that data can be placed onto the processor bus. Now suppose I want to read the status bit, that is SN value is to be read by the processor. Then what should happen? The valid signal that is coming from the keyboard will come as 1, and this will result in setting the SN value as 1. Now this SN value also needs to be sent to the processor. For it to be sent to the processor, the D0 line of the processor bus is used. Here also we have a 3-state driver which is initiated by again using an AND gate, which should satisfy 4 conditions. That is, again the read signal should be 1, master ready signal should be 1, it should be the address of the keyboard right now which is being decoded by the address decoding circuit, and the only difference is the A0 bit should be 0. That is to differentiate between reading the status bit or reading the data from the data in register. If A0 bit is 0, then this line will also be 1, and thus this driver will be initiated, and the SN value available over here can be placed on the data bus of the processor, and it can be sent to the processor. Now the only remaining signal is the slave ready signal. The slave ready signal can be made 1 only during 2 possible cases, that is either when I want to read the status from the input interface or when I want to read the data available in the data in register. In either of these cases, the slave ready signal needs to be 1. That is why here I have an OR gate, and this OR gate, when it becomes 1, it will activate this 3-state driver, and the value 1 can be set as the slave ready value, and it can be sent as a handshake signal to the processor. So this is how this circuit of the input interface works, and whether I am reading a data value or whether I am reading the status value, both are initiated by using some 3-state drivers, and similarly the slave ready signal is also sent to the processor through a three-state driver. And all these can be possible only if a number of conditions are satisfied. That is, the processor has issued a read signal, the master is ready, that is the processor himself is ready, the address that is available on A1 to A31 lines of the address bus of the processor is currently that of the keyboard, and this A0 line which should contain a 0 for reading the status value and a 1 for reading the data value. So next we will discuss the parallel port that can be used for connecting a processor to an output device. Here we will see a printer. So first we will discuss the different components involved. Here also we have the device, that is the printer, the output interface associated with the printer, and the processor. And the different connections are the idle signal that is coming from the printer to the interface, which indicates whether the printer is currently idle or not. Then there is a valid signal which is used to indicate whether the data to be printed is currently available in the interface or not, and the data lines coming from the interface to the printer to supply the data that is to be printed. On the processor side, similar to the input interface, we have the data bus, the address bus, the read bar, write bar signal, and in the case of a printer it will always be equal to 0 because we are doing a writing operation from the processor to the printer. So it is a write operation, so this signal will be 0. Then there are two asynchronous signals, master ready and slave ready signal, to indicate whether the master, that is the processor, or the slave, that is a printer, is ready or not. And this is the output interface. It contains the data out register which is used for holding the data that is to be printed. Then there is an S out bit which is the status bit associated with the printer. It is set to 0 when nothing is being printed or when the printer is not ready, and it is set as 1 when the printer is ready to print some data. And also here also there are some address decoding circuits and timing control circuits which are not shown in this diagram, but they are there over here. So these are the different components that are associated with the output interface of a output device connected to a processor. So now we will see the circuit that is involved for an output interface circuit. The different components that are used remain the same. That is, we have the address decoder which contains lines coming from A1 to A31 of the processor. The A0 bit is, or the A0 line is specifically used to differentiate between reading the status value or loading data to a printer. And then we have the data out register which is the buffer register that is used for storing the data that is to be printed. Then we have the handshake control which is used to initiate the idle and valid signals associated with the printer. So the working is initially the printer is idle or the printer may be busy, and when the printer becomes ready to print some data, it will set the idle signal as 1 and it will inform the output interface circuit. And when the idle signal becomes 1, the handshake control circuit inside the output interface will set the S out bit as 1, which was initially 0, and now this information needs to be passed on to the processor. This is done by using the D1 data bus line of the processor bus. But here also we can see, similar to the input interface, I have a 3-state driver which is to be initiated by using some signals, and it is connected to an AND gate, and 4 conditions need to be satisfied. That is, since I am reading the S out bit from the device to the processor, the read signal needs to be 1, the master should be ready, that is the processor should be ready, so this value should be 1, the address that is available on the address lines of the processor should currently be that of the printer, then this value will also be 1, and the A0 bit should now be 0 because I am reading the status bit. And if all these four values are 1, I can read the status bit, and thus the S out value, which is now being set as 1, will be placed on the processor bus D1 line and it will be sent to the processor. Now the processor understands that the printer is ready for printing. So what will the processor do? The processor will send the data that is to be printed through the data lines of the processor to the output interface of the printer, that is they will be now available inside the data out register of the output interface of the printer. Now how it will be taken to the printer himself, for that again here we can see there are some 3-state drivers present over here for loading the data from the data out register to the printer. And how are these 3-state drivers activated? Again some conditions need to be satisfied. Here since I am doing a writing operation, that is data is taken from the processor to the printer, that is why the read bar write bar signal should now be 0, that is this value will be 1. The master himself should be ready, so this value will be 1. The address on the address lines should be correctly decoded, that of the printer, so this value will be 1. And the A0 value should be 1 to indicate loading of data from the processor to the printer. And if all these four conditions are satisfied, this AND gate will be activated and I can load data from the data out register to the printer himself. And along with this loading of data, the valid signal will also be set as 1 by using this line, and the valid signal will also be sent to the printer indicating that the data is now coming from the data out register to the printer. And here also we have the slave ready signal, which is initiated either during the read status operation or the load data operation. That is why here we have the OR gate, which is again activating a 3-state driver when either status is to be read or data needs to be loaded to the printer. So this is how the output interface associated with the printer works. We have already discussed the input interface circuit and output interface circuit. Now we will combine them together into a combined interface circuit. That is, the input and output interface circuits can be combined into a single interface circuit, and here the overall interface is selected by the higher order 30 bits available on the address line of the processor. In the input and output interface circuits, when they were operated separately, we used 31 bits for identifying a device. Here we'll be using only 30 bits, and the rest of the 2 bits, that is specifically the address bits A0 and A1, will be used to select whether I want to read from a data in register or write into a data out register, and also to read the current status values S in and S out. So we will see the combined interface circuit. This is the circuit diagram for the combined interface circuit of input and output devices. The circuit remains the same, only they have been combined together. That is, here you can see the data in register, which has got input lines coming from a keyboard, and the input lines are indicated as PA0 to PA7. Here we have the data out buffer register, which will have output lines going to maybe a printer, which are indicated as PB0 to PB7. Then here I have the input status bit value, which is being set, that is the SIN value can be set, and it is set using the valid signal coming from the keyboard. It is indicated or denoted as CA over here. And similarly the handshake control circuit, which is used to deal with the idle signal and valid signal of the printer, which is indicated as CB1 and CB2. Here we have the S out value and S in value, which is activated using the 2 3-state drivers. Then here I have the 3-state drivers for the data in register and the 3-state driver for the data out register, which are initiated again using the different AND gates. So here I require 3 AND gates. One AND gate for setting the value of S in and S out, one AND gate for setting the values of the data in register, and one AND gate for setting the values of data out registers. process, and the signals remain the same, that is master ready signal, read bar, write bar signal. This signal will be 1 when I am reading the status bits or when I am reading something from the keyboard, and this signal will be 0 when I am writing something to the printer. Then here I have the address decoder. As I mentioned before, here only 30 lines are used for indicating or identifying a device, that is A2 to A31. Then I have the two lines A0 and A1 which are used to differentiate between the different reading and writing operations, and the different combinations of these A1 and A0 are taken as RS1 and RS0 to decide whether I want to read an S out value or read an S in value or read something from the data in register or write something from the data out register to the printer. So this is the circuit diagram for the combined input and output interface circuit. And also finally the slave ready signal, which is set by using an OR gate, which combines the values coming from these three AND gates. A more flexible parallel port can be created by using bidirectional data lines. That is, till now all the interface circuits that we defined either had separate input lines or separate output lines or combined input and output lines. Now we are going to define a new parallel interface where there are bidirectional data lines which can be used for both input and output purposes. And more flexibility is achieved in this circuit by using program control. We can use some lines for input and some lines for output purposes. And to do all this, some new circuitry components are added into the circuit. One of them being the data direction register, which is used to specifically control the data out register. So here we are going to define a new general parallel interface with bidirectional data lines. So the number of data lines required can be reduced considerably. That is the main advantage. So this is the diagram that shows the general 8-bit parallel interface. Here we can see there are 8 bidirectional lines P0 to P7, and they can be either be used as input lines or as output lines based on requirement. So here we have the data in register and here we have the data out register. The data in register works in the normal fashion itself. The data out register's working is controlled by a new register called a data direction register. When some data is to be sent to an output device, whatever data is to be sent will depend upon the values inside the data direction register. That is, this register will activate the 3-state drivers of the data out register, and if these drivers are activated, the data lines will act as output lines, whereas if these drivers are not activated by this data direction register, then these lines will act as input lines for the data in register. And here we have two other components, that is a status and control component, which indicates two lines C1 and C2. They indicate the valid line in the case of an input interface and the valid and idle lines in the case of an output interface. And here we have the register select component, which includes various values like my address. My address is used to indicate the value coming from an address decoding circuit. Then we have the read bar, write bar signal, which is 0 for a read operation, 1 for a 1 for a read operation and 0 for a write operation. And this ready and accept signals indicate the master ready signal and the slave ready signal. And here we have RS0, RS1 and RS2, which indicate the A0, A1 and A2 lines of the address line of the processor, which can be used to select the working of these various components, that is whether I want to read the status bits or whether I want to write from a data out register or whether I want to read from a data in register. And here we also have the interrupt signal INTR indicated, which can be used for interrupting the processor if required for performing various input output operations. So this is a general parallel 8-bit interface which is more flexible compared to the combined one or a separate input or output interface. Till now we were discussing about parallel ports. In parallel ports, as we have already seen, n number of wires will be present for communication between the device and the interface. If it is an 8-bit parallel port, then there will be 8 lines or 8 cables for communication between the device and the interface. It is relatively simple in design, and the advantages, it can be used for connecting devices that are physically closer to the processor. Now if I have a case or scenario where I want to connect devices which are far away from the processor compared to the parallel port, I can go for a serial port. Serial port is used for connecting the processor to IO devices that require transmission of data one bit at a time, and these serial ports communicate in a bit serial fashion on the device side and a bit parallel fashion on the bus side. That is, on the device side, the data will be transferred one bit at a time and the data will reach the interface, and from the interface to the processor, the data will be transferred in a parallel fashion. So there is some kind of a format conversion required. That is, there is a transformation between parallel and serial formats required in the case of a serial port, and this will be achieved using some extra circuitry. That is, some shift registers have to be used which have a parallel access capability for converting the serial data into parallel data. And the advantage of serial ports is they can be used for connecting devices that are farther away from the processor compared to devices which are nearer to the processor. This is the circuit diagram for a serial port. The components remain the same. The only difference is the introduction of two new shift registers, the input shift register and the output shift register for conversion of data from serial to parallel or parallel to serial form. So here we have the data in register for receiving input coming from an input device, and data out register for sending the data to an output device. The only condition is the data should be in serial form. So consider, for example, I have a serial input device over here. The data coming from the device will be in one bit at a time. It will come to the input shift register. Once all the data have been received inside the input shift register, it will be converted to parallel form. That is, this register is actually a serial to parallel register, and that data will be supplied to the data in register. From the data in register, using the previous three-state drivers, the data can be sent in a parallel form to the processor bus. Similarly, the data that is to be given to a output device will come parallelly from the processor through the D0 to D7 lines to the data out register, and from the data out register it will be placed into the parallel to serial conversion output shift register, and from this shift register it will be taken out serially to the corresponding output device. The rest of the components remain the same. That is the status and control signal circuit, the register select and chip select circuit with the different components which have been already discussed in the previous slides. So this is the circuit diagram for a serial port. Serial interfaces require only fewer number of wires compared to parallel interfaces, and thus serial transmission is more convenient for connecting devices which are physically away from a computer. Now the speed of transmission of data over a serial interface is known as bit rate. The bit rate can be very high or very low depending upon the speed of transmission of data. Now in order to accommodate devices with different ranges of speeds, a serial interface must be able to use a range of clock speeds possible. That is, different devices may have different speeds. So depending on the speeds available, the serial interface must be able to adjust and work accordingly. Now As we have discussed till now, any input output device is connected to a computer by using an interface circuit. So what is the current scenario now? We have to design separate interface circuits for every combination of an input or output device and a computer? No, it is not possible practically. So a practical solution will be to develop some kind of a standard interface and standard protocol so that any input device or any output device can be connected to a computer properly, and thus such kind of interfaces are known as standard input output interfaces. How to accommodate these standard IO interfaces? That is, only a few number of devices can be connected to a processor bus directly. That is, there will be only maybe one or two or maybe three or four slots available for connecting an input output device directly to the processor bus. So, as a solution, the motherboard usually provides one more bus that can support more number of devices or more number of input output devices, and such a bus is called an expansion bus, and this processor bus and expansion bus are interconnected by a circuit known as a bridge, and whichever extra number of input or output devices are there, they can be connected to the expansion bus, and this expansion bus will be connected to the processor bus through this bridge. Now, the design of a processor bus is very closely tied to the architecture of the processor, whereas the design of the expansion bus can be made a uniform standard by based on the requirements of the different interfaces of the input output devices. That is the purpose of introducing an expansion bus. In this diagram, you can see we have the processor bus that is indicated over here. The processor bus is used to connect the processor and main memory, and from the processor bus I have introduced one more bus. This bus is called the expansion bus, and this expansion bus is connected to the processor bus through a bridge, and this expansion bus is known as the PCI bus. On the PCI bus I can connect all the different kinds of extra input output devices that I want to connect to my processor. For example, here you can see all the additional memory components, the Ethernet interface that is for providing internet facilities, and if I want to connect any USB devices, and if I want to connect any hardware hard disks, for all that different kinds of interfaces may be required. All these extra required interfaces can be connected to this expansion bus. Inside a motherboard I can have one or more expansion buses. Here I have the PCI expansion bus, then again I have the SCSI expansion bus. Different number of expansion buses are possible. On the PCI bus I have the Ethernet interface, the ISA interface, etc. On the SCSI bus I have the disk interfaces. So this is how I can use different interface standards inside a computer system for connecting different kinds of IO devices to my processor. And they are called the standard IO interfaces. Different number of standards have been developed for the expansion bus. Some of them have evolved by default. For example, the IBM's ISA bus or the industry standard architecture bus. And there are also three widely used standard IO interface buses, which are the PCI bus or the peripheral component interconnect bus, the SCSI or SCSI bus, that is a small computer system interface bus. Then there is the USB bus or the universal serial bus. So these are the different kinds of expansion buses which are possible inside the computer, and they are called standard IO interfaces. With this, we come to the end of this presentation. Initially, we started off by discussing the different interface circuits that are possible for connecting IO devices to a processor. First, we discussed the parallel ports or the parallel interfaces, one input interface and an output interface. Then we discussed the combined interface circuit, which involves both input as well as output operations. Then we made it into a general bidirectional interface, and then we studied about serial interfaces or serial ports, and finally we discussed the need for standard input output interfaces, and we talked about three important standard interfaces, that is the PCI, the SCSI and the USB interfaces. With this we come to the end of this presentation. Thank you.